Hey, this is Mr. Mitchell. Let's talk about gravity. Here are some gravitational questions. Go ahead and write them down. Gravity. You know what gravity is. This apple here falls and the force of gravity makes it go all the way to the ground. But something you might not know about gravity. Gravity actually is a measure of acceleration. Notice what we have here. We have some time-lapse photography. We have the apple right here at the top and takes a picture after, I don't know how long, maybe a tenth of a second or something along those lines. And notice what is happening. We have a short little gap right here between. We have a bigger gap between apples in this frame. And we have an even bigger gap in this frame. This apple is actually accelerating, and that's exactly what happens whenever you drop something. The first tenth of a second is not as fast as the last tenth of a second. That's why if you drop something from an airplane, say a quarter, it could be going so fast by the time it gets down to the ground that it could really do some damage if it hits somebody, because it is accelerating. So because gravity is accelerating, that fact leads scientists to call gravity a force. Now, the strength of a gravitational force between two objects depends on two factors, and you can figure out what they are because they're right here. Mass and distance. The closer things are and the heavier they are, the more gravitational attraction they'll have. That's why the gravity, this is usually going to be talking about very big objects, like a person at their desk and their desk are two objects, but whenever you compare them to like celestial objects, no matter how big the fella is, he's not going to be having that much gravitational pull. But when you do have things of truly big mass, like planets and like moons and things such as that, that's when it's easier to tell. And the bigger the mass, like this is bigger than this, the bigger the mass, the more gravitational pull it will have with other objects. You know, Jupiter is supposed to be the biggest the biggest planet in our solar system. There are moons that they have that apparently were just objects flying out in space, and it got close enough to where it began its orbit around Jupiter. It's big, so it can attract more moons in this case. So the closer the objects are, and the bigger the objects are, the more gravitational pull you'll have. Now, one interesting note is, say you have one object that is bigger and the other object is smaller. You still get the same amount of force as if two of them were bigger. It's kind of interesting. If you double the mass of one, it actually doubles the gravitational pull of both. And the farther apart you get, the less gravitational pull you have. Don't know why they have these long arrows here. It should be short. The acceleration due to gravity is something called g. And you can see g in this formula right here. And this acceleration due to gravity is going to be the same on Earth. 9.8 meters per second square. So anywhere on Earth you go and drop your apple or drop your coin or drop whatever, it will drop at 9.8 meters per second square. So you may recall this formula here. This formula here measures force. Force is mass times acceleration. Hey, we know the acceleration of anything dropping on Earth. The acceleration of anything dropping on Earth is going to be 9.8 meters per second square. So we can find the force going downward. The force going downward of any object as long as we know the mass. So force going downward, that's the force of gravity pulling upon that object, which by definition is its weight. Sure, you could have this formula, which is basically coming from this formula, and have F here, but its weight, which is measuring. So this F equals mass, force equals mass times acceleration. Another way you can put that, if you're dealing with dropping objects, free-falling objects, is W equals M times G. W is the weight, which is the force going downward. M is the mass, of course, just like it was in this one. And G is the gravitational constant, which is going to be 9.8 here on Earth. So, why don't we do a calculation here? Oh, a stray mark. Sorry about that. But anyway, if you have the mass of something is 75 kilograms, then all you have to do is multiply it times 9.8, which you see right down here, and that will give you the force or the weight. Now notice what they did here. They put force instead of weight, but it's the same thing. It's the force going downward. So if you happen to see it F equals mg or W equals mg, it's the same thing. And that would translate, once you multiply that out, to 735 newtons. Just so you'll know, 1 newton equals, what is this, 0.22 pounds? So if you were to calculate something, like say you had the mass of an apple. If you had the mass of an apple here, you could formulate that into pounds. Once you finish your calculations and get the number of newtons, then multiply it times 0.22. I'm not sure what 735 times 0.22 would be, but it doesn't matter. We just know that we'd have to multiply it if we wanted to find the pounds. Objects fall at the same rate. So if you were to drop a golf ball and a bowling ball at your shoulders, they would drop at the same time. They would hit at the same time. They have the same rate of fall. All of it's going to be 9.8 meters per second squared. And you know, you can see how people wouldn't believe this at first. And years ago, reportedly, Galileo dropped 2 balls, cannonballs of different weights, and they ended up hitting off, dropped them off the Leaning Tower of Pisa, and they ended up hitting reportedly at the same time. And they should, because these two masses hit, they travel at an accelerated at the same speed. Now, some people have a tough time with this concept. Gravity actually pulls harder the heavier the object. And whenever you step on the scales, that's what you're seeing. Because if it pulled the same way, oh, I better get rid of that. If it pulled the same way, then everything would weigh the same. So if it actually pulls harder on this bowling ball than it does this golf ball, then why do they still drop at the same rate? What balances it out is that the heavier an object is, the more inertia it has. You know, inertia is desire to stay still, or its desire to keep moving, in this case stay still. So scientists think that even though you have more weight of some things than other, gravity pulls on it more, they still drop at the same rate because inertia drags these big things down. Kind of a heady concept, but that's what the deal is. There's another interesting aspect of gravity. Happens when you shoot an object horizontally. For example, you have a bullet that is coming out of the gun, and you have a bullet that you're dropping right beside the barrel of the gun. If you drop the bullet, it will hit the ground at the same time this bullet hits the ground. Let's say it takes 2 seconds. Even though you're firing this out of the gun, the gravity is still constant. So it may hit 500 yards away, but it will still hit the ground at the same time. Isn't that interesting? So, let me show you what that does here. And, well, I say let me show you what that does here. We have another slide before we get to that. Weight and mass are related, but they aren't the same properties. Weight is the force of gravity on an object, and mass is the measure of matter. Weight is actually the force of gravity, so it is measured by spring scales. You hang something here, gravity's pulling it down. Mass can actually be measured by this balance beam here. You put some kind of mass here and some kind of mass here to even it out. Now, pounds, of course, are going to be in weight. But let's say Elvis, and I'm not sure why I ended up picking this one, Elvis is on these different planets. He will have the same mass. I mean, he's not going to suddenly lose mass going from one planet to another. But according to where I got this, on Earth he was 255 pounds. But notice he's a different weight on every single other planet. And on the Sun he weighs 7,000 pounds. And it's because the heavier the planet, the heavier Elvis weighs, because there's more gravitational pull there. Now here's what I was going to get to on the shooting a gun. This is actually the reason why we have things in orbit. Let's say we have this pitcher here. This pitcher is pitching the ball. If someone were to drop a baseball to the ground, it would hit about the same time this baseball would hit, 100 feet later. So they hit at the same time, just like we saw with the bullet. Now, what happened, and it's going to be about 5 meters in the first second, and then it accelerates from there. So what if this pitcher could throw faster and faster and faster? Is it possible, since the earth is turning underneath him, and since there's going to be a curve to the earth at some point, is it possible for him to throw the ball so fast that it actually would fall at the Earth's curve? Now here's what I mean. If it takes 5 seconds, 1 second to fall the first 5 meters, how fast would you have to throw it to where once it falls 5 meters, the Earth has moved? And that's not physically possible for a baseball player to do, but if you were to be able to throw a projectile at 8,000 meters per second, 8,000 meters per second, that's 17,700 miles per hour. If you were to do that, it would never hit the ground. And that's exactly what's happening when you have satellites in orbit. When you have satellites in orbit, of course they're falling. It's just that they're going so fast that by the time they do fall, the earth underneath it has moved. Isn't that something? That if you get something fast enough, if you get it fast enough, it continues falling, but the earth underneath it has moved. So as a result, it's going to just orbit around the earth. And that's exactly what happens with satellites. They're not up there and the laws of physics suddenly change. That's not what's happening. What's happening is it's just going fast enough, at minimum 8,000 meters per second, to be able to do that. We have found that 11,000 meters per second is too fast. That's what you might call the escape velocity. If you have a rocket going over 11,000 meters per second, it will escape the orbit of the Earth and end up going out into space. So anything traveling between 8,000 meters per second and 11,000 meters per second is able to do that. Now, what if you are a person who is in that spacecraft? It looks like there's no gravity, but there is. It's just that you are traveling at 8,000 meters per second, just like your spaceship is. So even though you don't have a reference point around you, you are truly falling, just like the spacecraft is. It's just that you're moving so fast, you're going to be in orbit and just never hit the ground unless you have some kind of slowdown of speed. So I hope you've learned a lot about gravity.